Good morning.
Good morning, everyone. Sorry for the delay in getting here. I don't know what happened. I was uploading or going into Zoom and the window disappeared and I couldn't find it. It's probably somewhere already open. Did it say I closed a meeting or anything?
No.
Yesterday I actually closed one. It was weird. I got locked up and my only choice was to leave the meeting and end the meeting. And so I just sort of left it there, went looking around on my desktop for other windows where I could work, and it wasn't there. So I had to do that, and then came back and opened it up, and it said I had actually quit the meeting. Exciting adventures of old people using technology. Tough. So opened up another test for you guys. It's in some sense it's an optional test. It's really not. I mean, you'd be crazy not to take it. Let's put it that way. But what I'm doing is you had seen on my syllabus that I was going to drop one lowest online test. Well, what I did was introduce another test, and I'm going to now drop two lowest online tests. So in some sense you don't have to do it, but it does cover material in the final. And therefore you'd be crazy not to. You do get a number of trials to do it, and only your highest grade counts. And if that grade turns out to be lower than one of your other grades, then it's not going to count. So
you say you're going to drop two lower tests?
Two online tests, yes, sir.
Oh my God, thank you.
You're welcome.
That's nice. Oh, and good news, Professor Younger.
What's that?
I'm fully vaccinated.
Right, good job. Now you're relatively healthy and less likely to get someone else unhealthy. So that's awesome.
Professor?
Yes.
I have a funny lab experience I did in my senior year, if you want to hear it.
Yeah, go for it.
So in my senior year, I did take astrology, and the thing is, my teacher had us blow up these balloons to indicate how a star life cycle is and how big they can be as well.
All right, gotcha.
So since I was in front of the class, I had the super giants, and someone right behind me, one of my friends, had a giant star, but there was a problem. You want to guess what it is?
No, I can't imagine.
He didn't know how to blow up a balloon.
Are you serious?
Yes. So we end up giving him a white dwarf star so he didn't have to blow it up.
That's funny. I remember when the first time I tried to blow up a balloon, it was surprisingly hard. I remember getting pains in my jaws, but I was really young and small at the time. So I imagine the first time you ever encountered blowing up a balloon, which I don't know why it would be so late, but surely it was. Maybe he just didn't have a happy life. But yeah, that would kind of suck, because I remember blowing it up and it was like, God, my cheeks hurt so bad. Oh, that's great.
Yeah, well, we all did have a crack at him for that. He was smart, but just didn't know how to blow up a balloon.
Can't even laugh at that because I can't blow up a balloon either.
Oh.
Yeah. You just didn't have a happy life if you never blew up balloons.
Man, I run out of breath halfway through.
We had a professor back in East Carolina, a friend of mine, and his name was Edson Justiniano. I really liked him. He was a funny guy, but it was like he was pretty good at like almost everything that you interacted with him on. I mean, he knew like multiple languages. He had a good knowledge of history. Obviously, had his PhD in physics, and specifically particle physics, which was pretty impressive and stuff like that. But then I discovered that evidently he's not that inclined athletically, which you can't tell just looking at him. He didn't look weak or frail or anything like that. He's a good sized guy. But he was telling me, he said, I was trying to learn how to ride a bike when I was young, and they did it on a hill. He said, I was going down to the hill, and then there was a crossroad and an intersection, and there wasn't any stop signs or anything like that. So there was a chance I was going to get run over. And then on the other side of the road, there was a barbed wire fence and a bunch of cows, and all I could think was V squared over R, V squared over R, V squared over R, and I ended up flipping over the barbed wire fence and landed in the cow pasture.
That sounds like
that's the first problem. If you're thinking of V squared over R when you go around the curve, great. All right. Well, today we're doing chapter 24, which is life. And it's a pretty fun chapter. I enjoy it. And it's a lot of students, at least with my background, I know this is what happened, and a lot of students I find in this area have had similar backgrounds where their teachers rightfully just didn't want to deal with the headache of, you know, various parents in various communities raising a fuss about teaching their child evolution. So this is one of the few chances we get to really expose you a little bit to some of the nuances of evolution. I highly, highly, highly recommend you guys reading The Greatest Show on Earth by Richard Dawkins. I also highly, highly, highly recommend that you not read any of his other stuff, because other than that book, he's at least most of the stuff I've read that he's done, he is really offensive and a butthole to any person of religion or faith. So I would say leave all those other books out until you hear someone say the opposite. But right now, do consider reading The Greatest Show on Earth, which gives a wonderful case for all the or a lot of the evidence that we have about evolution, specifically talking about DNA, talking about fossil records, talking about all sorts of other records and evidence we have. So it's really awesome. But anyways, that's what we're going to do today. Does anyone have any questions before we get started?
No, sir.
Anybody want to know why v squared over r is relevant? You don't, trust me. All right, so let's what I'm going to do is I'm going to go ahead and share my screen, and we'll open up the wrongly labeled chapter 24, the terrestrial planets and Earth's moons. I think whoever they paid to make the PowerPoint just stopped actually typing in the titles beyond chapter 9, which I think was what terrestrial planets and Earth's moon was. But it did say chapter 24, so I know it's the right one. And then when you see the next photo, you'll know it's the right one as well. So this is on, like I said, life. Specifically, you know, how life came to be, what life needs, all that stuff is a whole different branch of science called astrobiology. And that's sort of what we're hinting at in this chapter, is to tell you about those types of things. So it opens up with, are we alone in the universe? And as I said, that is a question for astrobiology, and that's a question for astronomy. That's a question for philosophy. That's a question for a lot of different things. It's really interesting. And you've probably heard, for instance, of Drake's equation, at least on the Big Bang Theory, if not other places. But Drake's equation is sort of like an engineering type equation that I used numerous times when I was a structural engineer or doing structural engineering work. I actually have never been a licensed structural engineer. I just did the math. But anyways, with that, you have, like, for instance, you look in the Wood Products Association manual, and you are maybe using a 2x10 that's made of yellow pine, which is really the strongest wood there is. And it tells you a certain number, like the bending stress or the modulus or something like that. And those numbers are extremely important. Those are the ones that basically the American forest products industry has actually done tests on to make sure the wood does what it's supposed to do. And in fact, it's actually got a huge safety factor. That's why you can see so many old houses, like literally from the early 1900s, houses that are leaning over really badly but still are standing up. It's because there's a huge safety margin built into wood construction. But the way you are supposed to work with that number is you take that number and then you say, okay, well, this particular 2x10 that I'm using is actually going to be used as floor joists. Well, if it's going to be used as floor joists at 16 or 12 inches on center, then it's what we call a repetitive member. So you can multiply that strength by a factor, a correction factor, and that correction factor is like 1.1. If it's going to be used in a wet environment, we know that it's going to actually weaken over time due to moisture. So you then have to multiply it by, say, 0.92. If it's going to be submerged, partially submerged, so it can actually wick water up, then you're going to have to multiply it by 0.78. And you just slowly get all these factors that compound the actual effect. And that's what Drake's equation is. Drake's equation takes all these factors, like, the likelihood, what's the probability of a species living long enough to not kill itself by nuclear war, but long enough to actually communicate by satellite. All of the individual factors we don't really know, but we can take educated guesses at them and put together roughly the estimate of the number of intelligent life forms we would find in the universe. and it's down to a couple maybe in our galaxy, and maybe a few hundreds in the universe. But again, those numbers are all based on numbers that we don't know that well, so we could be far off. But the big thing is you don't get zero. Okay, that's kind of interesting. You don't get zero. It's kind of hard to get zero, strictly because there is so many stars with objects orbiting it, and then there's so many galaxies with stars orbiting it, and then there's so many various galaxies and clusters and all that. So the numbers are just really surprising if we don't have any other life. So that's sort of one of the stories of Are We Alone in the Universe, and what we do to think about that kind of thing. So if we're going to look for life, we need a real definition of life, and that is not actually as easy as you might think. A lot of things do the things that we think of as life, okay? And we want living objects, not living humans, but living things. We want them all to be considered in life, in the definition of life. So one thing is we take in energy from other sources. In the case of humans, we take it from food. We get some vitamin D and other things as well from the sun. And then we are able to survive on that energy we draw from other sources, and we reproduce. So that's sort of the lowest hanging fruit of what life would be, something that can reproduce and can take in energy from its environment to survive. Well, that fits, and that's really nice. And in fact, the virus actually meets that definition. Bacteria, all the forms of life that we know of meet that definition. But that might not be enough of a definition. In fact, virus is on the cusp of whether we consider that a life or not. So you got to take that into consideration. What are the other things? And obviously, when you start defining something as life, then it becomes a political and a moral problem as well. Basically an ethics issue, let's put it that way. So for instance, I love keeping my lawn looking nice. I really love it looking nice, deep green, and I like to keep it a little bit long so that it is really thick and lush feeling when you walk on it, and soft and stuff like that. But if I discovered that grass in general had a central nervous system and nerves and was feeling pain every time I cut it, and it wasn't like cutting a toenail or something like that, I would actually feel a little bit saddened by the idea of mowing grass, just because it's actually physically hurting a living thing. In fact, I don't know what I would do. So that's one of the ethical, moral problems when you go to define life. Are you going to define it so loosely that things exist such that they don't feel pain, but you could still be hurting them, and then because you're thinking of it as life, you're less willing to do the things that need to be done? Obviously, you can think of the big political issue, which is abortion, and obviously, at some point, somewhere between, and I'm not getting into that debate, I don't want to discuss that with anybody in the class, I don't want anybody else bringing up their beliefs on it, but somewhere between conception and birth, that original blastocyst eventually becomes a life. Whether that's the instant conception occurs or whether that's the instant it leaves the womb is clearly debatable. There's good reasonings for various dates and stuff like that. But you can see from that danger that there's clearly a big problem when you start saying something is a life. And that's part of the issue here. I once had someone post an argument that basically it was an anti-abortion argument, saying that Democrats are perfectly willing to kill babies, but they're not willing to go to Mars and accidentally kill a microbe because that's life. I get what they're saying, and if you really are obviously believing that life begins at conception, then abortion would be a horrible thing because you're killing innocents. But what they're saying here isn't quite right. There's a difference between what is life, what is living, and what is conscious and able to feel pain and stuff like that. So that's something that I'm trying to get at in terms of the definition of life that we need to take into consideration when we're thinking of a definition of life. So what is life? As a bare minimum right now, we'll use it as something that can reproduce, can derive energy from its environment in one way or another. They may even be parasitic, so that they're something that leeches onto something else and sucks energy from that other life form or whatever. That's fine too, and can reproduce. And that's the big thing. And as we'll learn when we talk about evolution, is it's got to be able to reproduce. And sexual selection is a huge factor for the ability to reproduce. If you come out as a male mallard duck, and you're not pretty, you don't have that beautiful green head, female ducks are not going to check you out that much, and you're not going to get to have your spawn go into the next generation. So that's one of the selection pressures. There's other pressures, survival of the fittest and stuff of that sort. And all of those things actually play a role in whether you can reproduce. So the weird thing is, right now, putting aside the definition of life, we know there are obviously numerous living things on planet Earth, and life itself is, at least in this form, is the only form we know of, and it seems to be carbon-based and really, really, really requires water. I haven't learned, and I don't read as much in the literature of this area as I would like to, but I have not learned of any alternative ideas about life existing without liquid water, though I suspect there might be some other solvents that could be used for a particular type of life. But I do know, for instance, carbon-based life is not the only possibility. Carbon, for instance, is in a very specific column in the periodic table. And the periodic table is ordered in such a way that anything in a particular column is very much like all the other things in that column chemically. So if you look immediately below carbon, there's silicon. Well, that's why people talk about there being silicon-based life, because silicon-based life has many of the same bonds and stuff like that carbon does. The energies aren't the same, but it's still a possible atom that could be used for life. So you could talk about silicon-based life. If you go further down, you'll see there's germanium, I think, strontium, and lead even is another thing in the same column. So, lead-based life, obviously, that would be a whole different scenario. But those are all real possibilities. So far, all we think about that I know of is carbon and silicon-based life. But our only example of life is carbon-based life. So we run from there, and therefore we look for the outputs of life on Earth and use those as indicators of potential life on other distant objects. And then we look for ways to find those indicators. But like I said, so far we haven't found, I don't know of anything that could live with any other solvent other than water. But water is super important because water has a high specific heat. So if your cells and your body is 70% water, it's going to be very hard for it to change temperatures appreciably without a huge amount of increase in temperature or increase in energy coming in or leaving the life form. It's also a really good solvent. It's a polar molecule, so it can do a lot of things that other molecules can't. So all of these processes that cells use, which cells seem to be the smallest part of life that is living, all these cells need water for that. And our life needs carbon as well. And in fact, they need carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus. And if you talk about humans specifically, I would add potassium on that, as well as some other things, because, for instance, sodium for sodium channels in your heart muscle, and calcium for calcium channels, calcium for your bone, iron for your blood, potassium for depolarization of your heart cells, your myocardium, that sort of stuff. So all those different elements are different for different species. But one of the most interesting things about life on Earth to me is the fact that it seems is the idea that it seems possible to start life without any divine intervention. It might be, and now we haven't proven that. That's not completely proven. I mean, it could very well be that we need some divine thing to come in and kick in. We don't know that, okay? But in 1952, Urey and Miller did an experiment where they basically took and they sterilized a glass tube, basically like a huge beaker type thing. And then they put in it water. And then they put in it the actual gases that were expected to be in our primitive atmosphere and even our secondary atmosphere later. But they put these things in it, And then they simulated the actual effects that the sun provides. So the sun provides light and the sun provides heat. So they actually, gave it access to heat, and they gave it access to lightning, to storms, right? And the way they did that was connected to a power supply with some spark plugs. And lo and behold, they came back after some period of time, not very long, by the way, and discovered that though they never put these things in the flask, they found amino acids and nucleic acids. Amino acids and nucleic acids, amino acids being the parts of what becomes proteins, and nucleic acids being the part of DNA and RNA. So these are the precursors to life. And in fact, they found, if I remember correctly, it's like 15 amino acids. There's 20 that are necessary for life. About, I think, 50 or 20 or some years later, they came back and put hydrogen sulfide in the atmosphere of this experiment using the same flask that they had before, ran the experiment again with hydrogen sulfide added to the atmosphere. And when that was done, it was actually discovered that 25 amino acids had actually appeared. So well over the number of amino acids necessary for life, at least life as we know it on Earth. So that's a really, really big deal. This is sort of the beginnings of saying origin of life could very well be non-divine, just something natural. The inhabitants, the location of the Earth, the things that were on the Earth, the chemicals, the compounds, the energy sources, lightning strikes and things like that, they are sufficient to make the building blocks of life, specifically amino acids and nucleic acids. And in that sense, self-replicating molecules are on the list. Some dude just pulled up and walking through my yard with a darn, I don't know what the crap he's doing, but he's walking around my yard with his phone. Anyway, it's weird. If my door rings, I'm gonna have to pause you guys for a second and come back and see what's going on with this dude. So I don't know what the crap he's doing over here. But anyways, we're back to the Eukarya experiment. So this was a first shot over the bow, if you will, of looking for the origins of life. A lot of people study that aspect of astrobiology, literally just looking for the origins of life. What could have spawned life? The earliest, or some of the scientists believe the earliest life would have formed in tide pools, and that was almost universal for a long time. But fairly recently, we discovered that there's huge amounts of energy and huge amounts of life, various varieties of life at ocean floor vents, basically vents to the inner Earth at the floor of the ocean. And those things, though they're in some cases super acidic, in other cases super alkaline, in many cases super hot, 70 degrees Celsius, that sort of thing. And what we find is that that area, which we thought would be completely without life, turned out to be actually inundated with life. And now many scientists think that that could have been the first locations for life.
Younger, your doorbell rang.
Yeah, hold on a second, everybody. Let me see what's going on here. Crap, this is such a pain in the butt. Escape. Hold on just a second, and I'm going to stop sharing just a second so I can get my access to my screen. I apologize for that. But they're doing some maintenance stuff on the house. All right, so what I was talking about was, let's go back to sharing the screen, was with the Eukarya experiment, we were able to show something that looked like the beginnings of origins of life. That's a really big ongoing question. Some people, like I said, think that it might have occurred at subfloor or sub-ocean vents. Other people thought it occurred in tidal pools. And then a very small number of people think it may have been via something called panspermia, where basically life could have been brought in on a comet. But that just pushes the question to somewhere else. Where did life come from? So most people don't like that one. And there's literally zero evidence that life was seeded on our planet from a comet. So just put that out there. That being said, this experiment does show that life could form. We haven't really worked out whether it was in tidal pools or in subfloor vents or that sort of thing, but the vents are a good option. And we have found fossils, for instance, of stromatolites that date to 3.645 billion years ago. And those fossils were stromatolites that would be in tidal pools. So that's some of the oldest life we know of. However, we have other things of life that might be as old as I think it's 4.1 billion years, maybe 3.8, 3.9, something like that. So we have other types of life as well. This is those vents that I was talking about below the surface of the earth or of the ocean, geothermal vents, and they're basically have access to volcanism and all the heat there. And we found these tube worms and all sorts of stuff, life living down there. And you would really think it's sterilized because of the high temperatures, but it's not. Here's a picture of a tidal pool. The good news about tidal pools is it has all the energy from the sun because it's shallow, and it has all the water. But the other one, once we discovered that things could live in those extreme environments of that geothermal vents, then we had an energy source other than the sun. You didn't have to have the sun anymore. And we found life, for instance, in areas where the water is 125 degrees Celsius. We found tardigrades that could be frozen for decades, maybe even centuries, maybe even millennia, and still come back to life. So there's things that live in extreme alkaline conditions. There's things that live in extreme acidic conditions. There's things that live in extreme dryness. There's things that live in extreme wetness, all sorts of stuff. Here's some of the stromatolites that I was talking about. They suggest there was life more than 3.5 billion years ago. So all this life seems to have occurred, no later than about, we think the Earth was maybe 4.6 billion years old. So if you go to 3.5, that's about 900 million years after after the planet was formed. And maybe even less, maybe 700 million years after the planet was formed, did life start to form. That would have been the earliest of life. The coolest thing I think about life in general is that, and this is something that people don't necessarily know, Carl Sagan made a really good comment about it, picking on Star Wars, which I don't approve of, Star Wars, good Lord. Star Trek, which I don't approve of, where basically he was talking about Spock being half Vulcan, half human. And Vulcans are actually from an entirely different planet, and of course would have an entirely different origin of life, entirely different DNA, entirely different evolution, unless it happens to be that our way is the only way, and that all the little parts of our way is the only way are also the only ways. It's very, very low probability that a Vulcan and a human could get together and actually procreate at all, much less procreate with something that could produce offspring. And that's sort of when you first start finding life that has evolutionarily diverged from one another. The first thing that happens is that they can still reproduce, but they will reproduce life that's not able to reproduce. And then the next thing is you just can't reproduce at all. And in fact, Carl Sagan, this is the kind of funny part, Carl Sagan used the argument basically, and I'm probably mixing up fruit to make it sound a little less disgusting, but basically you're more likely to get pregnant from a tomato than you are to get pregnant from a Vulcan. And that's because all life on Earth is cousins. We're all cousins of every living thing on Earth. And we didn't put all that together initially. We put together a lot of things. We're related to a lot of things. And then when we started discovering DNA and genetics, it turned out the DNA mostly supported everything that we had already found. There were a few things, minor issues that we were a little bit backwards on. But generally speaking, DNA and gene studies showed us that we were right on the money with evolution, and showed us, in fact, that we are all descended of a common ancestor. In other words, there was one species, somewhere maybe 4.5 billion years ago, maybe maybe 4.1, definitely not 4.5. I said that way too early. Maybe 4.1, maybe 3.8 billion years ago. That species went on to create all species. Okay, that species would have been something more like a single-celled organism, or something like that. Though it's not, it's not an ant, it's not an ape, it's not anything like that. And we'll talk about that in a second. But all because of these discoveries of extremophiles, we've got all these different sources where it could happen. What we do think is maybe early life was Cyanobacteria, and that does, if you look at the DNA. Basically, when one creature evolves into another, it doesn't just erase its DNA and start over. it starts with the DNA it has. So it's got all the DNA of all its ancestors in its DNA, and then it builds on that in some sense. And because of that, you can see by how much overlap there is on DNA, you can see how far back a particular species diverged from another species by where their DNA stopped matching one another, stuff like that. And it turns out that, you know, everything has some part of the DNA that's identical. And that part is what shows us that that life came from one common ancestor. And that part looks like exactly what we see the majority of it being in cyanobacteria. Cyanobacteria is when oxygen started to be produced. And since we had cyanobacteria that could photosynthesize, that actually released oxygen. And you can see how the oxygen went up in our atmosphere, roughly from about 1% of the current oxygen levels at about 3.2 billion years ago, hit around 8 or 7 or 8% about 2.9 billion years ago. And then right around 10 billion years, or excuse me, right around 10% of the current level around 800 million years ago. So this is roughly 800 million years. And we can see right in here when it reached about that 20% of the current oxygen levels, that's about as low as we could actually breathe. So humans would probably be only likely to survive on the order of about 700 million years ago or so, roughly in this area, somewhere between, you know, higher than 10% of the current 20%. But not necessarily as high as the 30%. So somewhere in here. And then about 0.7 billion years ago, in other words, 700 million years ago, the first vertebrates, and then arthropods, excuse me, were the first ones. And then vertebrates would have came up about 4 billion years ago, and then flowering plants and age of the reptiles. So that was really how life started to make use of oxygen. Oxygen wasn't necessarily all that prevalent in the early atmosphere. So this is the tree of life, and it's showing specifically the primate branch of the eukaryote Animalia. Okay, so basically what we say is this, right? Whatever this is the common ancestor to all of us. And as you can see, this species had some children, and these children, one branch, not unlike what we, you know, if you read the Old Testament or the Quran or something like that, you'll see that there was Abraham, and he had 2 generations of children, and they split off and became, you know, different things. Obviously, one of them being the Jews, the other one being what ultimately became Muslims, but would have been just Arabs even before that. So this is just like a regular family tree. That's what I'm trying to point out here. These cousins became, and I can't read these words that well. It looks like an aqueducts. Aquifix. I can't tell if that's an F or a D there, but anyways, Thermologa, Bacterianides, Cytophagia. All of these are the bacteria branch. Spherochetes, which are not unlike the things that come from syphilis, gram-positives, green filamentous bacteria, so on. So that's the bacteria branch, and these are prokaryotes. So they are without, they are proscribed. Proscribed means forbidden. So proscribed nucleus. So these things do not have a nucleus. Archaea are like bacteria, but they're quite a bit older, and we call them Archaea because they're sort of like archaic. They're old, and they don't exist anymore, of course. But you can look in these. At least that's my understanding. I could be making a mistake. There might be some new discovery, that Archaea, that I didn't know about. But I've always talked about Archaea as fossils we found of life that seems to have descended from bacteria, but wasn't quite to the eukaryotic stage. So I could be wrong about that. There may be new research, but I'm telling you, all these things, as you can tell, are descendants of the same common ancestor. Now, when you get here and this breaks off, of course, you see another common ancestor. This is a common ancestor of the Archaea and the Eukarya. Just like right here, this is a common ancestor of everything below it. So the green filamentous bacteria to Thermologa, all of these have a common ancestor that's that. Now, when you break off here, you could go this way to the Archaea, but you could go this way and you get fungi, which are eukaryotic, so that's cells with nuclei, plants, ciliates, flagellates, trichomonads, which I think is the stuff you get from eating raw pork, microsponda, diplomata, diplomonids maybe, animalia, which is what our group is, slime molds, and that's a bad word. I don't even want to try to say entomobia, something like that, and it shouldn't be bia. But anyways, when you break off the animalia branch, what you see now is this right here. This is a common ancestor to plants, fungi, and animals. Whatever the crap it is, it's our uncle. Okay, and obviously, if you go a little bit above that, then another one of our uncles spawned plants, fungi, animalia, and ciliates. And if you go further, it spawned all those things plus slime molds. And if you go further, it spawned all those things plus that word that I can't pronounce, intamoeba, I don't know. And then before that would be flagellates and so on and so forth. But when you go off the animalia track and stick to, say, the primate branch, you'll see that lemurs break off. We had a common ancestor with lemurs. That would be right back here. Later on, lemurs had a common ancestors, of course, with us, which would be the same one. But the tarsier has a common ancestor that would be in this gap with us. And the New World monkey would have a common ancestor with us that would be in this little greenish turning into yellow. And the Old World monkey would have a common ancestor there. And in fact, what we see is the most recent animal with a most recent common ancestor to us is the chimpanzee. Again, this does not mean we are descended from chimpanzees. It means that we have a common ancestor. So there's a great grandfather creature, and I might not have said great enough. I'm not really sure. And that great grandfather figure would have been something that's not unlike a gorilla and something that's not unlike humans. And some of its children became gorillas, and another branch of its children became humans. Or excuse me, not gorillas, chimpanzees. If I go further back, then the same thing happens with gorillas. And then if I go further back, then I can get orangutans. And before that, I get gibbons. And before that, old world monkeys, so on and so forth. That's just super interesting to me. Imagine, I mean, we literally are cousins with broccoli. Or with, you know, slime mold and bacteria and spherochetes and all that stuff. That's amazing. And it's all because of evolution. Okay, so evolution, what I want you to understand is evolution has a random aspect to it. That is absolutely correct, but it's not the thing that's been mislabeled as. People say, you know, humans and life forms forming from evolution is like having a junkyard for aircrafts, and then you walk in one day and a tornado picked up all the pieces and formed an aircraft out of it. That's just pure randomness at work, and no, that doesn't happen. Okay. Now, what can happen is you can randomly throw stuff up in the air because of a hurricane or a tornado or something like that. And then if you go and take someone like, and this is not the best of analogies because it obviously leads you to believe in a divine being. But you could have someone that walks through and selectively chooses the parts that the tornado or hurricane threw up in the air and chooses the ones that go together and slowly puts them together. And then another tornado comes through and more parts are observed. And then some grand engineer looks at the parts, knows what they are, puts the ones that work together with the ones that already has. And then slowly from that, you can form an airplane. That works. Okay. And that's not unlike evolution in that it has a random component that makes random selections, or excuse me, random changes, but it has something else that makes selections. That's intelligence. Okay. And it's not necessarily intelligence of a life form. It is brute force. You survive if you have this advantage or you don't. Okay. So that's really the part that's not random. And that selective pressure that they feel, that the life form feels, is what makes it not random at all. So we end up getting a finely tuned living species over time. Oh, by the way, I did mention about 500 million years ago is the Cambrian explosion. That's when the vast majority of fossils we have started showing up. That does not mean that was when life started. That just means life evidently did something special around that period that made fossilization a little bit easier to happen. Okay, so we've got a buttload of fossils. That did not mean there weren't fossils before. In fact, we have older fossils than 500 million years ago. Remember, I told you 3.645 billion years ago with a B. We actually have fossils from that of Stromatolites. So we know that's not the case. But just to keep you in the know, the Cambrian explosion is a big deal, and it puts basically a lot of life onto the fossil record immediately. Okay, and immediately is a geological time frame. So you know it could have taken hundreds of thousands of years, even on the order of tens of millions of years, to build that. But the main thing is around that 500 million years ago, we start seeing fossils, and that's because they were able to make fossils. And for instance, you know, people often say you can't disprove evolution, and you absolutely can. If you couldn't, then it wouldn't be a scientific hypothesis, and it is a scientific hypothesis. And that's the argument they made in that Ben Stein movie. Ben Stein. God, I can't remember what it's called. Expelled or something like that was some movie they made, and it was basically just an attempt to say evolution is not real. Or doesn't exist or something like that. But anyways, that's not true. One thing that's often planted is show me a rabbit in the Precambrian and you've disproven evolution. So if you look in the Precambrian, if you look in the soil record and look for fossils and find a fossil of a rabbit of some modern well-developed life form, okay, period. It doesn't have to be a rabbit, in other words. Anything that's well-developed, multicellular, got articulating limbs and stuff like that, if you find that thing in the Precambrian, you have dispelled evolution. Okay, you have disproven evolution. So there's lots of stuff you can do that with. So all these things basically became other things because of the selective pressures applied to them. So let's talk in terms of these various bacteria. You know, some bacteria, cyanobacteria, had photosynthesis. Well, that might have developed photosynthesis because it had a buttload of light around, and that gave it an advantage over these other species in the past, the bacteroids and stuff like that. Therefore, it developed this photosynthesis, and because of that photosynthesis, it had an advantage over other forms of bacteria around at the time. And slowly but surely, the forms of bacteria around would become predominantly cyanobacteria and lesser of the other types of bacteria. So this one would more or less take over that particular area. Later on, cyanobacteria could produce proteobacteria, and that was a descendant of cyanobacteria. And if it had some advantage over its other types of species of bacteria in the area, then over several generations, that bacteria would become the majority and the other bacteria would become the minority. That's really how it works. What we know is life actually came on land not too terribly long ago. In fact, I think I thought I saw it here. At the end of the heavy lake bombardment. No, that's that. That's this. The new species exploded about 500 million years ago. Maybe it'll say it later. But anyways, what we know is I think around 250, 300 million years ago, somewhere around that is when life started to come out of the water. So everybody's agreed that life probably had its origins. The people that don't are possibly the ones that believe in panspermia or something like that. But generally, the vast majority of scientists believe life began in the water, and it started to make its way onto land in the ballpark of 300 million years ago, somewhere like that. And in fact, one of the great pieces of evidence that evolution has for itself being a valid theory is Tiktaalik, this creature you see in the top right here. Tiktaalik is a species that was basically designed by biologists, meaning they literally imagined what that species had to look like, what its skeletal features would be, what its head would be like, possibly what its skin would be like, all because they knew there had to be an ancestor of it that they had been studying, and then there had to be a descendant of it that they knew of as well. And they put the pieces together and said, okay, well, here's this descendant and here's this ancestor. In order for evolution to take place, this ancestor has to develop this, this, and this. so that this descendant will have this, 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 and this. And they said, okay, and that would have to be in this time frame. And then they looked at the physical geological record, or the historical geological record, and said, where would those conditions that life would need to be on, where would they be at that 250 million, 300 million year ago mark, whatever the Tiktaalik mark was? And they predicted the species existing. And they said you should find it in Canada, and you should find it in this layer of soil, okay? And lo and behold, they went out and they discovered Tiktaalik. Okay, that is a huge feather in the cap for evolution, and it's not that big a deal for evolutionary biologists, because we know the record is huge. Okay, the fossil record alone is huge, and the fossil record's putrid compared to the other types of evidence we have. But this Tiktaalik was a really big deal. And in fact, we found it exactly where it was. And it's one of the first creatures that would have crawled out onto the surface of the earth from the water, specifically probably looking for food, expanding its horizons to get more food, that sort of thing, and was sort of comfortable in both environments. Okay. That's when life goes out onto the land. Then you start getting other life on land. You can get plants, you can get trees, you can get insects, all sorts of cool stuff. The big deal about evolution, the random part about it, is the mutation. So there's this neat thing about genetics and about DNA in particular that people don't really get. 10 to 11, 15. Okay, 9:30 to 10:45. That's what. Okay, I was afraid I lost too much time with my visitor. So, anyways, the random part of evolution is the mutation. But here's two discoveries that have been made that are really a big deal. So one thing scientists have done is, we can look at cells. We can look at plant cells, and we found cellulose holding it together. And we can look at animal cells, and we can see that cells of animals have this bilipid layer where basically the fatty part, which is hydrophobic, is on the outside, and there's another fatty part here, and then there's a hydrophilic part in between them. So this hydrophobic part has a hydrophilic end, and this hydrophobic part has a hydrophilic end. And hydrophilic is likes water, whereas hydrophobic means doesn't like water. And that forms sort of the structure of the cell membrane, the outer skin of the cell. And that has been analyzed enough that we know exactly what elements and what molecules make that up. And we have created a cell casing like that synthetically, not with life at all. We made it completely out of molecules. And then we took the stuff from inside of a cell and plopped it in there. The Golgi apparatus, the nucleus, the nucleolus, all the little bits and pieces inside of a cell, we stuck them in there, and that cell did just fine. So we're starting to see some of the things that says life isn't as quote unquote special as we thought. Okay. Another thing we've seen, for instance, is you can take DNA, and it is what we call homologous, which is the word I was trying to come up with yesterday. I think homologous. Basically, it's homologous with the species that the cell comes from. So, for instance, if you take a cell or a bit of DNA, you can point to one end of the DNA being stuff that deals with the head. And then you can move down a little bit, and you'd find a chunk of DNA that deals with, say, the torso, and then other parts that deal with feet and legs and stuff like that. That's kind of crazy, right? But that really is sort of how the DNA is laid out. And they've taken that DNA, and to find out that DNA just does its DNA thing independent of what crap's where, they took a part of the DNA of a fruit fly that was coding for the leg of the fruit fly, or the foot of the fruit fly, and they transported it from that same spot of DNA to the head portion of the DNA, and lo and behold, the fruit fly was born with a foot sticking out of its head. Now that's sort of unethical and sick, and I hate the thought of doing that to that poor little fly. But at the same time, that is a huge proof of concept that DNA don't care what's what. It's gonna run its program no matter what its program is, even if its program screwed up by having a foot part and the head part, right? That's one thing. And just like the cell being made, the husk of the cell being made by humans and synthetic processes without life involved at all is pretty impressive. It turns out that DNA is not special from one species to the next. For instance, what was done was they took a portion of the DNA for a firefly that causes it to luminesce, to glow, and they put that into the DNA of, if I remember correctly, a tobacco plant. And God, there's some possibility that I might be mistaking this with a Simpsons episode. But anyways, they put that luminescence bit of DNA in this tobacco plant, and the tobacco plant glowed in the dark. Okay, so DNA is not even special from one species to the next, because you can literally take bits and pieces of DNA from other species and put them together and get effects that happen in other species and make them happen in our species. So that's sort of the amazing thing that we're putting together. And it's not that we're trying to degrade life. We're just trying to figure out whether it's all science, or if there really is, like, is there a soul? Is there a conscience? Is there something beyond the chemistry and physics of life that makes it cognizant of its existence? Or is it just the fact that your brain is a buttload of neurons, which are essentially wires? They're crazy wires in that they're sort of like a root from a plant. You know, if you pull up a huge dandelion from the ground, it'll have this long stalk, and then it'll have all these little tentacles sticking off of it, if you will. Well, that's what a neuron's like, only it's that way on both ends. So it's got this little narrow part, and then it's got sticking off both ends. And that allows the neuron to make a connection to many other neurons. And those connections, at least the most superficial level, we think are what allow our brains to make connections between diverse topics. So if you are like reading a book, let's say The Prayer for Olamini, which is one of my favorite books, and you're reading that book and you remember a specific statement that was made in it, and you relate that back to your chemistry class, there's probably some neuron connecting that portion of your memory to that other portion, stuff like that. And then your brain is just a ball of those things. And if you were to cut them up, you'd see just a bunch of those little neurons all sort of intermingled on each other. So is that enough? Is that enough to be life? Is that enough for us to be cognizant? Obviously, we don't see that kind of structure, say, in plants, which is why I don't feel compelled to be sad when I cut my grass. Or when and I don't see it in, roses, if I go to cut off a bloom of a rose or something like that. And in fact, we do see other species with brains, obviously fish and gorillas and stuff like that. And those are the ones, the gorillas and the primate area, those are the ones that seem to have the highest level of consciousness, and they're obviously feel pain and stuff like that. So we really should be more morally upright in trying to deal with those. But guess what? Cows, which we clearly eat, pigs, which we clearly eat, and various other animals we clearly eat, they all have nervous systems, they all have brains, and therefore they're going to feel pain too. So all of this stuff is all what life is about. And the actual evolutionary part is that DNA, one thing you have to understand about it is DNA continues to work. DNA is not like I thought when I came out of high school, where basically DNA comes together, is formed, and that makes you the person you are, and then it just sits back in the background and doesn't do anything. Biology shows us that DNA continues to work. Every cell in your body has a nucleus in it, and that nucleus has DNA in it, and that nucleus in that particular cell has certain functions, specifically because it's in that shell. It's doing the thing that the environment that shell allows, and it's replicating itself. And every time it replicates itself, it has the potential of making a boo-boo. And when it makes a boo-boo, that boo-boo is called a mutation. Now, these mutations happen a couple times every million procreations of the DNA, and the vast majority of them do nothing. Like they're not positive or negative. They do in something, obviously, but they're not doing anything that we notice. Every now and then, one might actually give us, let's say, a frog with 5 feet instead of 4. Now, if that frog with the 5 feet is somehow, which clearly probably wouldn't be because it's more like a fifth wheel, literally, right? If that frog has some advantage over his neighbors, maybe the girl frogs in the area think that's kind of hot, and they're going to have a lot of sex with him, so he'll have a lot of offspring. Then if that was the case, because of that fifth leg. Wow, ooh. If you come back and look in that area where that frog was, the species of frog that exists was originally 1 out of a million had 5 legs. If you come back 10 generations later, you might find that 100 out of 500 have 5 legs. And if it's really advantageous, you might find after several more generations that 99 out of 100 have 5 legs. That's how evolution works. So it's got this mutation part that's purely random. It's a mistake, right? But if that mutation gives something an advantage, maybe it's a horse-looking creature that grows an extra vertebrae in its neck. Well, if that is an advantage and not a negative thing instead, then that advantage maybe gives that horse the ability to reach a little higher in the trees and be fed, and therefore it has an advantage over the others in that it can eat better. If you come back several generations later, the ones with that extra vertebrae will start to outnumber the ones without that extra vertebrae. And if you come back several generations later, it will almost be the only one there. Okay. And then later that mutation occurs again, and now it's got a second extra vertebrae. Over time, you eventually become a giraffe. So that's really it. And this selective pressure is the part that's not random at all. That is the part that says, with nothing but the actual facts to support it, if the facts say that because this animal has this mutation, it can either eat better or it can attract more females of the species or more males of the species, anything that gives it an advantage over the other ones, then it will overrun numerically in short time. And your book gives you the equations necessary to do that calculation. I'm not making you do that, obviously, but it will give you a new species that's more capable over time. And we've seen this over and over again. We can see, for instance, when South America was attached to African continent, we can see species that were all one and the same when those two continents were the same. But then when they broke apart, they diverged evolutionarily. So if one of the species, for instance, ended up on a small island where food is not that plentiful, then its advantage would be towards the ones that are smaller because they need less food to survive. So there's something called island dwarfism, that when a species diverges from another species by being isolated on an island, they often shrink. So we can see species that look identical to other species but are a lot smaller because they evolved on this island. And we can see other species that for instance, maybe the African continent had this one particular type of fruit and the South American continent did not have this particular type of food. You will see that the evolution of the ones in the South American continent growing to be able to appreciate the new food that's available there. All sorts of weird little things like that. So that's very much not random. And that's what I mean by, you know, an engineer coming through and picking out the pieces that the tornado or hurricane blew up in the air and picking out the pieces that could actually be used and putting them together. What's picking up the pieces and putting them together in evolution is life. You know, what is your ability to survive and have kids? Because those are the two important things. Now, if you live a long time, but you're no longer able to procreate, you're just dead waste from an evolutionary standpoint, because whatever's happening to you genetically doesn't matter. It's not going to affect anything anymore because you're not going to have kids. So it's really amazing that humans live beyond years of being able to give birth at all, because evolutionary, there's no reason for us to live beyond. Now we can see in modern times, you know, if you look at old pictures, like in the, even the 1800s, that recent, people will have drawings that they made of their kids, and their kids look like little grown people. So they're literally just smaller versions of adults. They're dressed the same. They look the same. That's because at that time period, you had so many kids, you really didn't invest your life into them as much as we do now, because you're going to lose, you know, 6 out of 7 of them. Over time, we've gotten better at human husbandry, and we can take better care of our lives, of our babies, for instance. And there is an advantage because grandparents can help you with that, and parents can help you with that. So now there is an advantage to us living longer beyond our reproductive years. And, you know, that could actually, modernization could actually make us live longer. And we're seeing that right now. The life expectancy used to be 70. Now it's approaching 77. And in some, for instance, Lincoln, Nebraska, it's like 82. So all these things are other selective pressures, if you will, that allow us to become better species. So if grandma had the gene that made her a caretaker, okay, so that after she was no longer able to procreate, she was able to caretake her kids, and then maybe even her kids' kids, and they likely had that gene as well, somewhat. So that species that came from her might over time develop this maternal instinct or this caretaking instinct that makes people live beyond their birth age, beyond their ability to procreate. So that's sort of the neat things. All these things that you develop due to these mutations are then hereditary because they're on the DNA. So your DNA mixes with your partner's DNA, and then you have a child that has a mixture of your DNA and their DNA in some sense. So they have some probability of having that same mutation that you had. And if that mutation gives them an advantage, then over time, that mutation will be the majority of the genetic codes in the area. Okay, does that make sense to everyone? I'm trying to explain as much as I can in detail about evolution and how it works, and show you not the random part versus the actual random part. Again, I highly recommend you read The Greatest Show on Earth. A sort of cool extreme version of that is whatever species preceded the giraffe was born with this vasovagal nerve that we have as well. And this vasovagal nerve actually has to extend, if I remember correctly, from the heart all the way up to the brain area or the skull area. And then it comes back down to the heart area or something along those lines, something weird like that. And because it's on a giraffe, over time, that neck got longer and longer. So that vasovagal nerve became like 40 feet long. That is not a well-engineered piece of machinery, right? If you're going to go from the brain all the way down to the heart and then come all the way back up to the brain in some sense, when really all you needed was connect from one part of the brain to the other, then that would be a bad design flaw, okay? And that's what we mean by when people try to argue intelligent design. We don't say it's very, very really intelligently designed. We have all sorts of weird anomalies like that, like the cones and rods in our eyeball. They evolved from a spot on the body, say something that preceded our heads, that basically when light came in, it would see that light and see distortions, and it gave it a little bit of advantage. But that was a thing here where the rods and cones were pointing outward. Over time, that evolved into an eyeball, and guess what? It couldn't start over. So in our eyeball, the actual rods and cones point to our brain, and the part that captures light is the part that's pointing towards the brain instead of pointing to the hole in our eyeball. So it's a really, really badly engineered device. It's like watching TV through the wires from behind, right? That's what our eyeball is made like. So those are some of the weird things that we have as a manifestation of evolution, but it still exists because evolution can't just start over from scratch. Okay, so that's why we can sort of dispel the idea of, well, that and all the literature on intelligent design started with a book in which you could find typos where they changed the creator to intelligent designer. So it said it had some weird word where basically you can tell they forgot to erase a couple letters on the creator or God, and they had left on, say, the letter G and D from God, and it became Gintelligent Created or something like that. It literally is that kind of case. I'm not remembering exactly what the letters are, but if you read the transcripts from Kitzmiller versus Kitzmiller versus Dover, PA, which the ACLU has their transcripts online. I've downloaded them too, so if you need them, let me know. But you can read that, and you'll see that's really what happened. Is people were just trying to put their religious faith into the science classroom, which is, I mean, I get it. I mean, if that's what you believe, then you want everyone to believe it because you're so happy with your life. But it didn't come from scientists. It came from a bunch of people that wanted to make intelligent design the thing so that they could, bring religion in. That being said, there are scientists. Michael Behe, for instance, is a good scientist, and he knows what he's doing, and he completely locked onto it and has found things that he thinks are pretty compelling. I don't. I read his book, and his book got me interested in biochemistry, which is amazing because I was never interested in before. So I've read a bunch of stuff because of him. So I definitely credit him on that. But in that particular area, he just was kind of duped a little bit. So, anyways, this natural selection is really what does the non-random part of evolution, and it's just naturally selected by your ability to procreate, your ability to survive, stuff of that sort. And like I said, the female mallard duck needs to be impressed by the male mallard duck, specifically because the female gets pregnant and then she's out of commission for a long period of time while they're gestating. So, humans, for instance, we gestate for 9 months. So the female devotes all of her energy and time to this one pregnancy, and that takes her out of commission for nearly a whole year. The man can impregnate the female, and then tomorrow can, and maybe even the same day, can impregnate another female, and then the next day it can impregnate more. So the woman has all the female of the species, the thing that carries the actual birth, and I'm not just talking humans here, I'm talking everything, has all the power. That's why the males have to turn out prettier, because they're the ones that have to impress the one that's going to devote her life, or a year of her life, to having offspring. So beyond that, that is really the natural selection process. That's one of the ways that natural selection has chosen beautiful males, as opposed to the duck that happens to be able to fly and carry a machine gun, for instance. If if we found a machine gun wielding duck, we would it might have a advantage, but it's not as valuable as being pretty. So now, the other part about life is it requires certain elements, like I told you: carbon, hydrogen, oxygen, nitrogen. It also says phosphorus and sulfur. I told you some things that humans specifically need, like iron, potassium, sodium, that sort of thing, chlorine. But in general, all of these elements are necessary. And we know from the Big Bang that it produced hydrogen and helium, right? We do know that it probably produced a little bit of lithium, which is why it's got that blue stripe there, probably a little beryllium, it didn't show it here, and probably a little boron, but very small amounts. And in fact, some of those can even be destroyed by the processes of stars. So we might not even have a net positive amount of beryllium or boron from the Big Bang. So that
2 minutes left.
basically you just say hydrogen and helium. Yes, sir.
2
Thank
minutes
you.
left.
So this is what we call an astronomer's periodic table, and it shows where those elements come from. So it's a really cool thing to have. I'd really like to have one hanging up on my wall, as my friend Lisa Flack said as well. But this tells you where that stuff came from. We know that the high mass stars create these elements in their death knells, and then the supernova explosion can create the other ones that are missing, and then their explosion spreads that material out over space, but also the galaxies pulling that around, and pressure waves pushing those clouds into other clouds spreads that throughout the entire galaxy. So the galaxy is helping, and then galaxies colliding with other galaxies is helping as well, getting those elements out. So they're all playing a role in life existing. But even with those elements, and those elements being spread around space, you still can't have life in an intelligent way beyond a single-celled organism, really, without the time period necessary for evolution. So you need an energy source that lasts billions of years. That is where the low mass stars come in. So we need all that, and that's really the critical aspect. Carbon special, it obviously is sort of the backbone of our DNA. We have looked elsewhere for other bodies in our solar system, and basically we look for water, and then we look for what we used to think was the only way that methane could be produced was by life processes. We've now found natural ways, so methane's no longer the great thing that we thought it was for finding life. But these are some of the bodies we've looked at. We've looked at other bodies too. We have found the existence of previously more wet environments on Mars. We know of water below the surfaces of Europa and various other places. All of these are places we want to look for life. We've got various rovers on the surface of Mars continuing to look for it. We know Mercury and Venus are a no-show for life. If we have anything on Venus, it would be some really small organism, the extremophiles, because everything is so harsh in Venus. But Mars is probably our best one. But we also look for radio signals, very specific, important wavelengths to humans, things that we found fundamentally important. If we find signals on those frequencies, we're more likely to believe that came from a modern species. You can even see We look in the habitable zone, which is this green area where water could exist as in a liquid form. We do that for other places as well. This is the plaque on the Pioneer 11. There's another one as well. I think this one was on Voyager maybe. But basically, imagine trying to communicate with another species that's from an entirely different solar system, star system, and a different galaxy even. How would you communicate with them? There's no chance in heck that they're going to have the same language as us. So we had to use math. We've got binary down here to show 8. We've got the hyperfine structure of neutral hydrogen here, so they can understand that we are knowledgeable. We have our location right here and the relative distances to all the nearest stars there. So we basically told all the creatures where we live. And then we showed them that, in fact, from that star, we're the third rock from the sun, and this is the thing we just sent off that you just found, so on and so forth. So it's really neat looking at that stuff and thinking about how to communicate with foreign species. And there's the Drake equation. Here's some of the radio telescopes that we use for SETI, the search for extraterrestrial life. And that's it. We're done. We finished 1 minute late. That's okay. You guys, of course, if you have any questions, please stick around. But I want to tell you, I did open that other test. There's a test 7 now available. Again, I'm now going to erase your 2 lowest online tests instead of 1 lowest. So this one could be seen as one you don't have to do, but that would be crazy because the final exam includes that material. So I would definitely say the rest of this week should be spent on you preparing for your final exam and maybe taking that test 5 several times. You have until April 5th. April 5th, by the way, or excuse me, yeah, April 5th is what I said you had until April 6th, which I think is a Thursday, whatever that Thursday is, which I think is the 6th. That will be our final exam date. Okay?
You mean May?
What's that?
You mean May, not April.
Yeah, sorry, May. I don't know why I was saying April. So yeah, that May 6th, that Thursday, is going to be the exam day. You can, in principle, if you need to, take it on the Tuesday before, but you got to let me know early so I can set it up. You have to have Respondus lockdown browser working. You have to have Respondus monitor working. You should go back and do the midterm and see that you can now do that. If not, you're going to have to set up an appointment with the testing center sometime between Monday of next week to Friday of next week. Okay. And I'll make up a separate test for you if you're taking it there. You should still not talk to people. If you've taken the test before they did, don't talk to people because there will be an overlap and you'll give them an unfair advantage. But there are going to be different tests. So it's not that bad if you accidentally drop some information to them. But I would say don't do it because you're just going to hurt yourself. So unless it's your boyfriend, your girlfriend, your cousin, your sister, your mother, or something like that, then you're probably only helping them, not yourself. Everybody's free to go. Don't miss the test. Okay, there's a test. I think there's 2 tests open now. One's like due tomorrow or the next day, and then this one.
Hey, Professor Young.
Have a good one. Thank you. Yes, Tyler.
Professor Younger, I'm going to guess for chapter 13 and 14, which is the 7th test, it's going to have some of the previous questions.
It will, yes. All my tests are comprehensive, so I still beat the drum of chapters 1, 2, 3, 4, 5, 6, 7, 8, all those things.
Oh.
But the practice test has them too. So if you do the practice test, you'll get plenty of experience with it, and it can't harm you. In fact, I gave you 5 trials, I think, on this test. And it can't harm you because if you make lower than one of your other online tests, then that one will be dropped.
Okay.
Lower than all of your online tests.
Farewell.
All right. Have a good one, Tyler. Matthew, you have any questions, buddy?
Hold on. Let me get it up here.
I'll be right back and get my coffee refill.
Okay.
Okay, I'm back.
I think it is. Okay, I did that one. Okay, you were talking about 11 and 12?
About what? The chapters, you mean? Yeah, there was a test. It's either like due tomorrow or it was due yesterday or something like that. That covered chapters 11 and 12, and now test 7's up, and that covers 13 and 14.
Oh, I was focused. Oh God.
What's going on? What do you think happened?
I think it was due yesterday.
You think so?
Yeah,